corrosion resistance. So for application like marine, where we have to work with oil and water, so we require some materials which have a good chemical resistivity. Okay. Rapid manufacturing. So to make these parts, we should require a system. With the help of which we can reduce the part very rapidly, rapid speed. Then design freedom. So if I have a particular part, like with let's take an example of this frame. This is a drone frame basically. And if we go with the normal 3D printing, so what will happen? I can have, let's say, I am printed in ABS material. So overall the strength will be the same. Okay. So how I can have a freedom to design it like if I go with composite 3D printing, especially with the continuous reinforcement method, so I can manipulate my design. Suppose at the corners I want a much higher strength, but in the middle I require a moderate strength. So I can achieve that with the help of reinforcement method. So this gives me design. And the last is low volume production. So, like again, generally we require drone in a very low volume. Basically depending on your design. So, if some company have given order to a drone manufacturer, so generally they give like 150 pieces or 200 pieces. So it's a low volume production. So the composite helps them to prepare the complete drone with the help of these composite. Now, even composites, there are of three types in the additive manufacturing. One is the polymer matrix, which is polymer composites. Like you can have nylon plus carbon fiber, you can have PC plus carbon fiber, ABS plus carbon fiber. So here both the materials are polymers. Then we can have metal matrix composite. So basically, these are for the metals. So you can have different metals and you can merge them and you can create a unique super alloy. Okay. Then we have ceramic matrix composite (CMCs). So you can add ceramic with metal. Now, in polymer, so there are two type of matrix, or I would say composite. One is the composite in the form chopped form, like nylon, and with some chopped carbon fiber to it. Okay, like ABS and some chopped carbon fiber into ABS. So we call it nylon CF, ABS CF. Second method is where we have an advantage we can do a continuous reinforcement within the same part of carbon fiber or fiberglass or some other fibers. Okay, so this body is actually made up of the second one, that is continuous fiber reinforcement. So here we have a base which is a composite. It's the matrix of nylon plus chopped carbon fiber itself. Then, to enhance the strength, I can further reinforce between the parts. Let's say this drone body is of like 200 layers. The complete system has 200 layers. So I can introduce some 100% pure carbon fiber layers to it. Like at the bottom, I can up to 10 layers. I can do the reinforcement. Then in the middle, like 4, 5, 6 layers, I can do the reinforcement. And at the top further I can do the reinforcement like 20 layers or whatever I want. So in the between the layers I can add 100% pure fibers to it. So that this is what we call continuous reinforcement. So if you see this part, the base, that black is the base, and the white portion inside it, it's fiberglass. So we did the continuous reinforcement of fiberglass into this particular portion. So what are the properties that we have in chopped fiber or the continuous one? So you can get the isotropic properties in chopped fiber, chopped composite because it is mixed in the powder form. So you get the isotropic property. But here, when we talk about the continuous fiber, so we are reinforcing in a particular direction. So you can achieve the strength in that particular direction with whatever you want. So like this part. So what I the strength what I require is if I band it, so I can have a strength in this direction. I don't want direction in this direction. So here I can have it with the continuous carbon fiber reinforcement. So now, Mark is a technology which gives you the liberty to have a continuous fiber reinforcement. This is a US-based company. They have a patent on this technology. They are global leaders. So they have designed the system in such a way, like they have a base material, as I have said. So their base material is itself a matrix of nylon 6 plus short carbon fiber, and further you can insert a fiber in between. So in Markforged, there are four type of material. One is the base, which is onyx, nylon plus carbon fiber. Then for the reinforcement, you have an option for carbon fiber, for fiberglass, and HSST. HSST is also a fiberglass. That's HSST stands for high strength, high temperature. And last one is Kevlar. So where we want high strength, we can go with carbon fiber. Where we want high temperature resistivity, we can go with HSST fiberglass. And when we have we want some impact resistance, then we can reinforce our part with the help of Kevlar material. So now about the carbon fiber, it's superior in the strength. If I reinforce the part with 100% reinforcement, the tensile strength which I can achieve is up to 800 MPa. That means I can easily replace aluminum parts. Okay. So when I say to replace the aluminum parts, this doesn't mean all the parts can be replaced because it is a polymer and I have reinforced it in a particular direction. It's not a homogeneous one. So the parts which are having static load or somehow dynamic load, but that not should be not critical dynamic load. Only those parts can be replaced by this method. I can achieve the stiffness. So if you see this part, just try to bend it with the arms. Okay, and check this one. This is similar to this. This is the reinforced one. This is a basic one. No, it's not reinforced. It's only poly. That is nylon plus chalk. This is reinforced. So overall weight I can reduce this up to 70%, and then fatigue resistance there. Now you can reinforce it with different orientations according to the forces that are applied on the particular part. So let's say about this part, this one. So there is a curve here. So you can decide the orientation according to your application. So it will be continuous thoroughly. Even if you want it in a XY direction, you can do it. If you want it in a Z direction, you can do it. So So these are some testing protocols. So we have done all the tests here. So there is tensile testing, flexural testing, impact resistance, fatigue. Now there might be sometimes can be happen that your part will get failed. So these are the points. Maybe there will be a fiber breakage during the printing. So the method is like that. There are two nozzles. Uh, from one nozzle, you can print the base material, and from the secondary nozzle, you can have the reinforcement of the particular fiber. So fiber does not stick directly to the base material. There is a glue out in the outer layer of that, and as it is a continuous fiber, so it just lay down continuously, and at the end of the layer, it cut it down, and then it again it starts from the next layer or that previous layer. So maybe during that continuation sometimes your breakage can be happen. So if that happen, then there are chances that your part can be failed. Then of course there is a challenge for interlayer bonding as well. Okay, if the bonding is not proper, then might be the part can get failed. Matrix cracking, it's similar to that. So there can be friction inside the part. Then fiber matrix debonding. So if that bonding between the base material and the reinforcement material is not proper, so it can get failed. So after when you can print the part, you can go for a testing and you can visualize it as well. So through the optical microscopy, scanning electron microscopy, thermal analysis, X-ray, so you can do everything. So it is just like your actual specimen, what you have in the metal. So you can here create the part. You can test it on. So the overall scenario is like this is the replacement in some scenario for the metal parts. Now talking about the industrial application. So for normal prototyping, your normal 3D printer can work, but for industrial application, these composite came and then jigs and fixtures. So you can directly make your jigs and fixtures with this printer because in jigs and fixtures there are no critical load. Okay, so generally companies are making this in metal, and there is a huge timeline for the fixture only. So they generally having a timeline of 2 months or 2.5 months. Here you can have it in some 8 hours or 10 hours. You can have the actual part with. Then robotic and effectors. So you can have robot grippers. You can make it with this printer. Automotive brackets you can make. Aerospace and unique components. So they require lightning weight and high strength parts. So you can directly make with this material. Then biomedical devices. So now there is a new application is there, which is orthotics and prosthetics. So if you have seen the artificial limbs, so earlier people are making it from the conventional method, but now we are replacing them with the composite 3D printing method. So we can directly print the socket, the entire socket, or the limb cover of upper limbs, and we can have that. So we are using some material like this is nylon 12 plus glass film. This is a different technology. It's not FDM. It's SNS technology, which is a powder based. So that limitation that we have in the FDM in 26 fiber that we cannot have the isotropic strength all over the part. So we can achieve it in SNS technology. So this is the part. Artificial limb center Pune is using this machine to make the limbs. The same have a branch here in Faridabad, Alinco. They are using it. They are printing and they are people are using it. This is 11. So it can you can bend it and then you can Now the limitation of this method is the build volume. So we don't have a capacity to produce larger part in composite. We right now we can print up to 1 meter only with the help of composite. And when I say the reinforcement one, so we can achieve up to 500 only. So this is the limitation. We cannot print bigger parts. Material cost, of course. So the carbon fiber one. So the material cost is very high. Like if the 100% pure fiber for 50 grams, we have to pay 15,000 rupees, which is very costly for the base material, which is a composite. So if you have a good composite in the market, so it comes around one spool of 1 kg of spool is 25,000 rupees. So it's a costly method. Matrix temperature limitations. So the temperature range with the parts can withstand, it's very low in terms of composite as of now. If I have application where I can have a temperature of 150 degrees Celsius, so these parts can work. When I go beyond 150, these parts cannot sustain. This is a 3D printer. We call it Mark II. The resolution can achieve up to 100. Then this is the basic bed size that we have. In X we have 320, in Y we have 132, in Z we have 154. So this is how the printing goes on. So it's a simple FDM process. Then in base material, we have an option for Onyx FR as well, which is a flame retardant material. So for that application also you have a material. Then we also have nylon white. So it's a non-abrasive, and if you want to have some colors, you can get it through dye. Then we have Onyx ESD for the electronic devices. So we can use ESD material as well. So this is a 7XS fully assembled robotic arm which is made of this onyx material without any reinforcement. This is a robot arm and effector. This is also a tooling application, and without any reinforcement we have achieved it. This is the part. So without the reinforcement also it's having a good strength, the base material, as it consists of chopped carbon fiber. So you can check these are the data sheet that we have. So that yellow portion is the Kevlar. So if you see, this is our software where we decide at what layer we have to give the reinforcement. This is the simulation. you see these circles, so you have a liberty to reinforce according to your application. How we can decide where we want to have the carbon fiber or Kevlar or HSST fiberglass. So where there is a tension, you must go with carbon fiber and HSST fiberglass. When there is a compression, you have to go with carbon fiber. When there is a bending, go with carbon fiber. When there is a impact, go with HSST fiberglass and Kevlar. When there is a heat deflection, then go with HSST fiberglass. When we talk about the cost, so the carbon fiber is the most costliest material we have. So economically, you can go with fiberglass. This is again aircraft bracket. We have enforced it with carbon fiber, also with fiberglass. The white portion we have seen it's fiberglass. It's a brake lever. We have enforced it with carbon fiber. So this is basically you can see here we have added the fibers. Few more applications like this is a gripper jo, it's a robot and effector, piston lifting tool, clamp head. This is another machine having a bigger grid size and even you can use it in the field as well. So the environment doesn't affect this machine. So you can even it's a plug and play machine. So in the deserts, in the rough terrain, you can use this machine. So there is no sophisticated environment required for it. So earlier it had created some boundary walls, and now it is doing the reinforcement. So to do the reinforcement, you must require some boundary walls, which you can do in the slicing software itself. Another application. So the video is all around like you can replace your soft tooling with this composite 3D printing. And there is also one plus point is during the printing you can put the inserts. You just need to pause it, just place the metal inserts and resume it. So during your printing only you can have an advantage to do the inserts. So these are the application of Onyx FR for electronic applications. Where assembly, electronic assembly, PCB assembly. So we require ESD materials. These are the few accounts that we have. We have supplied the solution to this. NASA is there, SpaceX, there was G, Facebook, Google. So these are primary customers. Now, this is basically a comparison uh, take an example of this. This is a MRO solution. So basically, for maintenance and repair applications, people are using this as a tool because there is a huge timeline to get the spare parts or the part that are using MRO application. So they are designing it and they are printing it at their own. So this is a case study. The Innovation Center they have a problem of turbine product life cycle. So they have printed it in few hours, and whereas the conventional method is they are getting the part done in 3 to 4 weeks. So they have saved like $8,000 during this. Then this is another one case study. So they have saved 100K euros in, and 8 months. This is you can check that what is the actual strength that we have in this. Another case study. So this is a automation equipment for CNC machines. They have made this black part with this composite printer and then replaced the metal. So this is a chart basically to give you a comparison with what material you should have for ESD. Like we have a aluminum of the left side, so it is conductive, and the onyx, what is the base material, so that is insulated. So we require something in between. So that is why we have introduced onyx ESD material. So these are the case study for ESD material. So it's a PCB assembly frame. Uh, Generally, it took them to make it in 1 month. With the help of this, they have reduced the cost, and the contractor demands for 100 pieces at least to manufacture it. But in 3D printing, they can have like 1 piece, 2 piece, 3 piece, whatever they want. So their 60% cost gets reduced with the help of this. These are the testing fixtures. So for PC fixtures, you require ESD materials. Now we have a turbo mode in the 3D printer. So when we are printing with composites, there is another challenge which is it is very slow compared to the normal 3D printing method because it is very tricky to print a composite materials. So they have introduced a turbo mode as well to get the print fast without compromising the surface skills. Then there is a software called Blacksmith within the system. It's a AI-based software. So while the printing, it analyzes each and every layer and it creates one optimized file after printing. So the next time you will print, your part can be optimized. There is a laser also which behaves as a 3D scanner basically. It's for inspection during the printing. After each layer, it scans it, and after welding, it gives you an inspection report. So whatever your K data is and whatever you have printed, how much accurate it is. So it's an inspection device as well. So that's it for the polymer composite. I have one more sample with me that is from MMC Metal Matrix Composite. I'll show you. So this is SS316 combined with bronze. So this is the MMC. We generally use it in aerospace applications where we require lightweight components having a higher temperature and a chemical resistivity. So what we can do, and of course we have to save the cost as well. So suppose this is a part of SS316, we can deposit some other material like tungsten carbide, nickel alloy, aluminum over it so that we can have a composite material. So the inner will be of SS, which is cheaper in economically, and to get the high temperature resistivity, we can have another material over it. So any questions?
So you have told about incorporating inserts while printing the material. But if we have given the command and the nozzle is following the path and you have insert the insert of it, so is it the nozzle will to strike that insert and going to push it outward?
Okay. So first we can do an insert. It can be like vertically with laser. Okay. Secondly, within the software, Classic software, you have an option for it. So after a particular layer, you can achieve it. So in the software itself, it will advise you, it gives some tolerances, and after what layer you should have to place the insert. So the software will guide you regarding the same. So there is a curve basically. In between you have to place it, and after the curve, the nozzle will again start printing. So there are no chances of collision. Machine part because the surface thickness is quite high. It's a machine part. Alloy. Okay, so polymer blank is just like this material, which is like this nylon plus short carbon fiber, and that reinforcement one is reinforced one, and the second one I am not aware of it. That so, is about the two incomplete polymers, and okay, we merge them to form a more superior quality of polymer that may be equal to hydrogen monomer, one percent. Right. So it can be possible in some printers, we call it oil printers actually, because they give you a liberty to have your own material, and within the parameters you can put in anything that you want. It's a research based building. So you can have that we have said that that material you can have that material and you can compose it. And now there is research also going on for polymer and metal composites as well. Because some of the requirements are like that. They need conducting materials, and in between some after few years, they require requires insulating materials. So there is research going on. You can have it very soon. You told about 4D dimension of the. Yes, so 4D is also coming. It's basically the four dimension will be the time. So after printing, the behavior or the property of the material will get changed. So we have tried few materials. So we have added some ions to a polymer, and with the time, the rate of attraction towards the metal it gets changed. So right after the printing, the rate of attraction was quite high, and after 2 hours, it is it's zero. So this is for the printing, which is coming. I think maybe down the line, after 2 years, you can see it. Any other questions? Thank you so much, sir, for coming here for detailed and insightful session. I would now request Professor Dr. Devendra Mohan sir and Dr. Smith sir, HOD, to kindly come forward and present our speaker with a token of gratitude and appreciation. We will now take a short tea break. After that, we have the hands-on training session lined up for all the participants. And with that, we would come to the end of session 2A2. And we look forward for another interesting and learning sessions on day 3 tomorrow. So thank you so much.
अरे आप तो सुबह